next part, so the next part is torsional oscillation or torsional vibration. Torsional oscillation. So for the shaft here, this is called the shaft. This is the shaft, and this is the flywheel. Okay, so whenever there is a flywheel that is attached to the shaft here, okay, so we assume that this shaft is of negligible mass. So we have to consider that the mass of the shaft is being neglected. Okay, and then the shaft will obey Hooke's law. Hooke's law. So from the diagram, as let's say for example here, if let's say for example we apply a slight turning moment or torque to the flywheel or to the disc, what happens is the disc will start to oscillate. I purposely have marked here as A, B, C, and D so that you can see the thing actually is oscillating angularly about its mean position. Okay, oscillating angularly about its mean position. Afterward, you will see that. Then we have to let that I to be the moment inertia, the moment of inertia for the flywheel. So the moment of inertia for a circular disc or a disc can be considered as mk squared or mr squared. So where m is the mass and k is the radius of gyration, which you should have done in your dynamics. So now if the flywheel is twisted, that means angularly displaced, as what I have marked here, angularly displaced, okay, through an angle theta, and then when it is being released, it will start oscillating about its mean position like this. It will start oscillating about its mean position. So at displacement theta from the mean position, the restoring torque, we say the restoring torque of the disc or the flywheel is actually equals to C multiplied by theta. The C is called the torsional stiffness. Is the torsional stiffness. So from here you can see the disc is actually now oscillating about its mean position. So we can see A and B and C and D. So they are actually oscillating about its mean position. Okay. So since restoring torque is equals to the product of torsional stiffness with the angular displacement is here. So whenever you displace or when it is being turned slightly, you will have an angle theta, which we call the angular displacement. Now, based on Newton's second law, also based on Newton's second law of motion, we know that for force, yes, it's equal to the product of mass and acceleration. For turning moment or for torque, it should be equals to the moment, the product of the moment of inertia with the angular acceleration. So I here, the I that you see here is actually the moment of inertia. So for a circular disc, you can consider as mr squared or mk squared. And alpha here is actually the angular acceleration, which is in radians per second squared. So from both of these equations, you can equate both of these equations, that is the restoring torque. You will have C theta is equals to I alpha. So when you were to rearrange this equation, you will have alpha over theta. Alpha over theta is actually equals to C over I. Remember, the C is the torsional stiffness. I is the second moment of mass or the moment of inertia. Why do we need to rearrange that so that we have C over I is equals to alpha over theta? Because earlier in our simple oscillation, simple harmonic motion, okay, we actually have already derived this part here, where the frequency is equal to 1 over 2 pi to the square root of angular acceleration over angular displacement. So based on the angular acceleration over angular displacement, so we can actually replace this angular acceleration over angular displacement by the torsional stiffness C over d, or divided by its moment of inertia. Okay, and also based on the simple torsion equation, which you should have learned, okay, in the subject of mechanics of engineering materials, where you have T is the torque and J is the polar second moment of area. So for a shaft, it should be pi d4 over 32. It's not over 64. 64 is the moment of the second moment of area about the x and y axis. J is actually the polar moment, second moment of area. So that is the moment of inertia, or the second moment of area about the z axis. Now T is the torque and G is the shear modulus, okay, or the modulus of rigidity. T is the angular displacement, or the angle of twist, and L is the length of the shaft. So when we rearrange that, we have theta is equals to TL over G multiplied by J. So our polar moment of inertia, that is pi d4 over 32. So here I have given you the list of the terms that we use. T is the torque, which is supposed to be in Newton meter. Theta is the angle of twist in radians. G is the shear modulus. J is the polar moment of area, or the polar second moment of area, or the polar moment of inertia. And I, this I here is actually the second moment of mass, or also known as the moment of inertia, but this is referring to the mass, and it is given as mk squared, where k is actually the radius of gyration. C is the torsional stiffness, which is in Newton meter over radians. L is the length of the shaft, and we know that restoring torque is equal to T equals to the product of C theta, and we know that theta also from this equation here, we know that theta is also equal to T L over G J. So when we substitute it into the equation T, which is equal to C theta, and your theta which is equals to TL over GJ. So you have this equation here. So that is the torque. So the torsional stiffness. So you have, from that you can arrive to this formula now, frequency. Okay, so I have told you that for oscillation or for vibration, the most important thing is we must be able to derive the formula for frequency, circular frequency, and the period time, or the displacement. Okay, so this is in terms of frequency, because we know that frequency equals to 1 over 2 pi square root of, okay, square root of the angular the angular acceleration over angular displacement. Okay, so when you manipulate the equations that we have earlier, you will arrive to this equation here. So that is quite a number of formulas that we have to remember. Okay, or when we replace the J, that is the polar moment of inertia, or the polar second moment of area, which is pi d4 over 64. Okay, so you will have the frequency as this here. That's what I have given here. Okay, that's all for the torsional vibration or the torsional oscillation. This is just the basic for torsional oscillation. So this again here you have exercises, so you can just try it. Thank you.